All right, Sadie, can I have you turn off just that front set of lights, please? Thank you. All right, so what we're going over today, guys, are the properties of compounds. Right? We want to look at what are some differences between ionic compounds and molecular compounds. Now that we know how to name them, okay, we want to look at how could we identify an unknown compound were it to be set in front of us. Right? Now, there are some obvious ways that we can do that. Okay. And we're going to need them because we're going to be doing a lab, hopefully late this week or early next week, where we will be given about a dozen unknown materials and asked to identify them based on only their physical properties. Okay, now, thinking back to grade 9 science, what are some physical properties? Density. That's the one you were going to say? Another one? Okay. Melting point is another one. Okay. Color. Okay, it's a physical property. What else? Boiling point. Malleability. Viscosity could be. Solubility, whether it dissolves in water. Whether it's ductility, okay, its ability to be drawn into a wire, okay, things like that. Yeah, all of those are physical properties, and every material has its own unique set of physical properties, right? That's what we're going to be using, okay, on probably Monday, okay, in order to identify all of these unknown compounds. All right, so we're going to learn the properties of the compounds, acids, bases, ionic, molecular. Okay, so pH is also a physical property. It's not one we listed before, but it is. Okay, understand how these properties can be used to identify a compound, and that, again, is going to be useful because you are going to design the procedure for this lab. All right, so you're going to figure out the set of steps, like step 1, acquire materials. Step 2, perform this particular test on all unknowns, record your data, etc. Okay, and then you would give description on how to perform that test. So you're going to be doing a lab design. That's one of the things we'll be working on this week, is getting our lab ready to go across the hall and actually perform it. All right. So, for compounds, okay, all matter has certain properties. Some are chemical, okay. Chemical properties are something we'll deal with later on in the unit. The main chemical property is reactivity, whether it reacts with something or not. Okay, and some are physical, right? We talked about some of those already. Okay, we listed color, density, melting point, solubility, all of those kind of things, pH. Okay, all those things can be used to identify something. All right. So, like we said, these properties can be used to distinguish between types of compounds. Now, we know that molecular compounds and ionic compounds have some things that are different because their bonds are different. Right? We said that ionic bonds are weak because they involve the switching of electrons. Right? And once those elements have those extra electrons, they're happy. There's no reason for them to stay together. If I put them in water, most of the time, what are they going to do very easily? Dissolve. Most ionic compounds are highly soluble. Most. Obviously, there are some exceptions. Okay? Once I put that material in water, okay, and it dissolves, what will the water do? Or now the solution, what will it do? That maybe distilled water wouldn't. Conduct electricity, right? This is probably the best way to determine whether something was an ionic compound or a molecular compound, is simply to put it in some distilled water, okay, stir it up, A, look to see if it dissolves, okay, and then B, check and see if the new mixture, the new solution, will conduct electricity, because only solutions from ionic compounds will conduct electricity. Molecular compounds, their solutions, even if they do dissolve, don't conduct electricity because the molecular compounds don't break up into positive and negative charges. Without those, there's no conductivity. Okay, so that is the single number one test, okay, to determine whether something is an ionic compound or a molecular compound. Okay, it never fails. There are other tests that are reliable most of the time. Okay, for example, all ionic compounds are crystalline solids at room temperature. There are no exceptions to that rule. All ionic compounds are crystalline solids at room temperature. Okay, now, are there some molecular compounds that are crystalline solids at room temperature? Yeah, sugar. Okay, sugar is a molecular compound. It's a crystalline solid at room temperature. Okay, so obviously if I was to do something like maybe make one of the unknowns salt and one of the unknowns sugar, okay, simply looking at them would probably not be a good way to tell which one was which, agreed? I mean, salt and sugar, if you look really closely, do look a little bit different, but I mean, they're white crystalline solids, both of them, right? They both dissolve in water, right? But in the end, one of them will conduct electricity and one won't. All right, so we're going to have this kind of process of elimination going on when we do this lab, okay, where, okay, these things are probably ionic. Oh, these two didn't conduct, so they're not. That means they could be these compounds, okay? Because obviously, I will give you the possible identities for everything, okay? What I'll do is simply put some containers out there that are labeled A through J or whatever, okay? And you'll have to decide whether A is salt and H is distilled water or B is whatever. Okay, that's kind of going to be what you guys are going to have to do. All right, so they are crystalline solids at room temperature because they have very high melting points, okay, often several hundred degrees. Right? Just putting salt in a pan and throwing it on the oven is probably not going to do very much. Okay, the salt probably won't melt at a temperature that would not already destroy your pan. Okay. Now, ionic compounds, like we said, will also conduct electricity when they are in solution, and that is probably, like we said, the most important thing to know, okay? Because it is the one test that will always tell the difference between an ionic compound and a molecular compound with 100% reliability. Okay, and like we said, the reason for that is because there's positives and negatives floating around the water. So you see in this diagram here, okay, when salt dissolves, here's the salt molecules, okay, when it dissolves, the sodium atoms separate from the chlorine atoms, okay, and the sodium atoms have a positive charge, the chlorine atoms have a ions have a negative charge. They're separated from each other, okay, and now the solution can conduct electricity because the electrons can flow from negative to positive. All right, and obviously, if I put too much salt in, what will happen? If I just keep adding salt to this water, it'll eventually what? Right, some of it will sit on the bottom. What do we call that? Okay, saturation. Yeah, if it reaches its saturation point, it means I can't make any more dissolve. Right? That's how I make Kool-Aid. Okay, I make sure I add sugar until it reaches the saturation point. Okay? In fact, what I usually do is make Kool-Aid with warm water so I can get more sugar to dissolve, and then I put it in the fridge, and when it gets cold, I can tell if I made it right if there's sugar sitting on the bottom. Because then it's just right. That means that the solution is saturated. Saturated, yeah. Okay? I mean, the definition of the word saturation is can hold no more. Right? So, I mean, if if you walked out in the rain, or snow, okay, you would eventually get wet enough that your clothes would begin to drip because they are saturated. They can't hold any more water, right? All right, so some examples here. This is what a typical ionic compound looks like under a microscope, okay? Regular kind of crystalline structure or shape, okay? Some of them are actually brightly colored, okay? And we'll go over a few of them because if you saw, let's say, a brightly colored green crystalline solid, it would be a dead giveaway as to what at least metal is in it, okay? Because some metals, when they get into an ionic compound, always produce crystals with a certain color, right? And so it'll be important to know which colors go with which. Okay, so here they are. Many ionic compounds produce solutions that are brightly colored, okay? And they also produce crystals that are brightly colored, right? So copper compounds are always blue. All right, so this is probably copper sulfate or something like that. Okay, has a very kind of bright blue color. Okay, this one here is kind of hard to see. It's faded, but this is cobalt, probably cobalt nitrate, and they're pink. Okay, and in fact, when you see cobalt nitrate crystals, okay, the solid form, they're actually red. Okay, but when they go into solution, they're kind of pinkish. All right, so cobalt compounds are pink, and nickel compounds are green. Okay, and there's kind of different variations on green. It depends what the nickel is with. Sometimes the nickel crystals can be very dark green, and sometimes they can be very pale green. It just depends on what it's bonded to. All right, so important to know those ones, because when you're trying to figure out the identities of some of those unknown compounds, some of them will be colored, okay? And that'll be kind of a dead giveaway as to what they are. All right, questions so far? Everyone's good with that? All right. All right, now molecular compounds, okay? Molecular compounds can be solids, liquids, or gases at room temperature. Okay, so they can be any state. They typically have lower melting points and lower boiling points than ionic compounds do. All right? Were you to put sugar in a pan and put it on your stove, don't do that at home, okay? But if you were to do that, you would be able to get it hot enough that the sugar would actually melt, okay? And then you would have, okay, you could do that because it's got a low enough boiling point, okay? I just don't recommend you do that because usually once it starts to melt, it also starts to burn onto the bottom of the pan and becomes almost impossible to remove, okay? So I don't recommend doing that. All right, so they could be liquids as well. So let's say we're in the lab over there and you're looking at all of the unknowns and you see that 2 of them are liquids, okay? If they're liquids, can they be any of the ionic compounds on your list? No, okay? So this is the process, again, that we want to go through. Process of elimination. These are liquids. They can't be ionic compounds, all right? Okay, we won't have any gases. It's very hard to put those in an open container and allow you to perform tests on them, so there won't be any gases in the lab, okay? Now, molecular compounds are not usually as soluble as ionic compounds. It doesn't mean they won't be soluble. Some of them are, okay? But many of them are not, okay? For example, oil. Okay, vegetable oil, butter, all of those things are molecular compounds. Okay, we know that they don't dissolve in water; they separate and sit on the top. Okay, some molecular compounds do dissolve easily in water. Sugar, we already said, is an example. Okay, alcohol, which is a liquid, okay, and a molecular compound, dissolves easily in water. Okay, if you add it to water, it dissolves. Okay, now we say dissolves. Can a liquid dissolve in a liquid? Actually, yes. Okay, it can. Okay, to dissolve actually means to just become one. Okay, so it creates a solution with only one visible part. I can't tell the alcohol from the water anymore. It's just a mixture. All right, everyone follow me there. Now, if I've got alcohol and water sitting beside each other, okay, they're both liquids, right? They're both molecular. They're not going to conduct electricity. How am I going to tell them apart? No, we're not going to do taste tests, okay? We can't do taste tests because A, you can't drink alcohol, you're not old enough, and B, because some of the compounds that would be in there, if you tasted them, it would be the last thing you ever tasted, okay? Taste tests are not allowed, okay, because they are very dangerous. However, is there another way to tell the difference? Nope, they're both going to be clear. It's going to be like pure alcohol, not something you would buy at the liquor store. Actually, alcohol and water are very close in pH. You might be able to tell which one was which. It's possible. But what's an even easier way? Smell. Okay? If I have a container full of pure alcohol and another container right next to it that has distilled water in it, there's going to be one very obvious difference. One is going to smell and the other is not. Okay? Water is got no smell at all. All right, so if you're just, kind of standing near them, you would probably be able to tell which one was which. All right, now, is it okay to smell unknown compounds? Yes, it is, provided you do it in the right way. Okay, snorting them is not a proper way, okay, to test the smell of an unknown compound. Snorting some of these compounds would be just as deadly as tasting them. All right, so we don't want to do that. Okay, what you do when you're testing something is you waft. Okay, so you stand, let's say the container's about right here, right? You would waft like this, and then some of the fumes would come to you, and you could inhale them. Okay. The danger is that one of the compounds you're going to get is actually already going to be dissolved in water for you, and it has a very strong smell. But if you were to inhale it directly, okay, it would knock you flat on your back, unconscious with a nosebleed. Okay, so it's not something that you would want to sniff actively because that would not be good for you. All right, I say that because it happened to me once when I was actually making a solution of that stuff. Okay, I got distracted and someone called my name and I leaned over to look at what they were talking about, and then I had a stuffy nose and I went, Boom. Okay, that was it. Okay, inhaled hydrochloric acid fumes up and unconscious and bleeding profusely from the nose. Not cool. Okay, not an experience I care to repeat. The person's reaction was, "Oh my God, what happened?" Because I just went right down. Okay, yeah. So then that's the next thing I saw was them looking over me, and they were like had blood on their hands. I'm like, "What happened to me?" But, yeah, it's all right. Okay. Other thing we want to be careful of, okay, obviously in the lab is how we handle this stuff. Okay, you don't want to get any of it on your hands. If you do, okay, you need to go and wash your hands in cold water for at least 5 minutes, okay, in order to get it off. Now, some of the stuff is perfectly harmless, right? Some of it is not, and since they're unknown at the time you're going to be working with them, okay, if you get any on you, you got to ask me, Mr. Goodhair, what do I need to do? And I'll ask you which sample was it, and I'll tell you either you need to go and rinse your hands off or you're fine. Don't be a baby. Okay. All right. So that's the reason why we got the conductivity of one, okay, and no conductivity of the other. We got positives and negatives in ionic compounds, and we've got no positives or negatives in the ionic ones. All right. So molecular solutions will not conduct electricity. Okay, molecular compounds which are soluble in water, okay, usually produce clear solutions. I mean, when you add sugar to water, doesn't change its color. I mean, it might get a little cloudy, okay, but it doesn't radically change color to something else, right? So they typically produce clear solutions. Okay, again, alcohol and sugar would be examples of that. They dissolve in water, but their solutions are clear. All right, acids. Okay, typically, strong acids are ionic compounds, typically. Okay, weak acids can be ionic or molecular. Right? But if you have something that is got a pH of like 2 or less, it is most definitely an ionic compound. Okay? Now, the reason for that is this. In order to have an acidic pH, you need to be able to lose or donate to a solution H+ ions. Okay? If you're going to donate H+ ions, you have to be an ionic compound with hydrogen listed first. Agreed? All right, so give you some examples here. HCl is hydrochloric acid. Okay, we could have HBr. Okay, bromic acid. We could have H2SO4. Okay, sulfuric acid. H2S. Okay, that's something that we hear a lot about in Alberta because it's a gas associated with oil field and gas operations. Okay. This one's really bad. Nitric acid. Why is nitric acid the worst on the list there? Because it has the most hydrogen. The more hydrogen ions that it can put into a solution, the more acidic it is going to be. All right, so these things tend to be, okay, this tends to be very acidic. In fact, you have to be very careful of that stuff. Even getting the fumes on your skin can cause chemical burns. H2O is not acidic because H2O is a molecular compound. Remember, the hydrogen ions share, or sorry, the hydrogen atoms share their electrons with oxygen. So yes, you're right. When it looks like this, it looks like it should be acidic. Okay. Hydrogen peroxide? Yeah, it's slightly acidic, yes. Okay, but it's different. It's a weak acid. Okay. The reason we say that water is also neutral is because we can write water like this: HOH. So there's, yes, a hydrogen, but there's also a hydroxide. This is the thing that makes things acidic, and this is the thing that makes things basic. Water has both, and they cancel each other out. That's why water's neutral. Yeah. Okay. All right. So they have H+ ions in them. The presence of H+ in a solution gives it acidic properties. Okay. Acids are usually ionic compounds and thus share many of their properties. They are crystalline solids, they are highly soluble in water, and they will be your best conductors of electricity. Okay? They'll be your best conductors of electricity when you do the conductivity test. All right? And that's because they very easily dissociate. Acids dissociate from each other very, very easily. Okay, acids taste sour. You're not going to be able to tell that because we're not doing any taste tests, all right? But obviously you know that things like lemons and stuff like that, okay, limes, they're acidic, they're sour, all right? They'll turn litmus indicators to acidic colors, right? We have, you know, the little pH strips that you can put in there, okay, and typically they'll make them turn orange to red, okay, indicating the presence of an acidic solution. Okay, acidic solutions have low pH, less than 7. Okay. Which is more dangerous, a strong acid or a strong base? Neither. They are equally dangerous. Okay. A strong base with a pH of 14 and a strong acid with a pH of 1 can equally hurt you chemically. Okay. They will cause chemical burns that basically would be indistinguishable, okay, from each other. Whether you got a chemical burn from a strong acid or a chemical burn from a strong base, you still have a chemical burn. Okay. They're very unpleasant. I had some friends that I had in high school. We were doing a lab with nitric acid, actually, in bio. I can't remember what we were doing now, but okay. They were on the volleyball team. One guy was the setter for the volleyball team. We were doing this lab, whatever. Okay, we finished the lab, cleaned everything up, and the guys didn't realize that their container had been open and they had been doing some stuff above it, and the fumes had gotten on their hands, which didn't immediately cause any alarm. It didn't hurt because it was fumes. They didn't notice. Okay, but a few hours later, they started developing blisters and stuff on their hands. Okay, they actually developed really bad chemical burns after about an hour or hour and a half or so, okay, on their hands that they didn't notice at the time. Fortunately, none of them touched their eyes in the interim. Okay, because had they done that, the fumes were actually in their skin and their hands. They would have probably damaged their eyes as well. Okay. It's too bad none of them went to wash their hands after the lab, which we were told by our teacher to do. Okay, they obviously didn't do it, so the volleyball team was without a setter for a little while. Okay, pretty hard to set the ball when you get big blisters all over your fingers. Okay, so you got to be careful with some of those things. All right, bases. Okay, bases are also, strong bases are going to be ionic compounds. All right, give you an example. This is basically one of your strongest bases. What's that stuff called? Chemical name. Na stands for sodium hydroxide. This is the stuff that's in oven cleaner. Okay, you ever smelled that smell? Okay, anyone ever used? No one ever uses oven cleaner now. Everyone's got a self-cleaning oven. Okay, but this stuff is the stuff that's in oven cleaner. It's in the white foam. Okay, highly corrosive. Okay, a strong base is just as corrosive as a strong acid, and it'll just eat all the crud off the inside of your stove, okay, or your oven. Okay, so typically bases taste bitter. Not that you're going to taste anything, but typically they're bitter, right? If you've ever accidentally got baking soda or something like that, soap, okay, has lye in it, okay, that's very basic, and they all taste kind of bitter. All right, and they will obviously turn litmus indicators toward the basic colors, which are usually blue to violet, and if it's really strong, it even makes our stuff turn black sometimes. All right. Their solutions will also conduct electricity because obviously this is a positive and that's a negative, and when it hits the water, it'll split. Okay. So your bases, your strong bases, will also be some of your best conductors of electricity. Okay. So if something is a base, it has an OH ion. Okay. If something is an acid, it has an H plus ion. So when you're looking at your possible identities, if this is on there and this is on there, okay, we should know automatically that these are acids or bases, or at least have the possibility to be. Okay? If we have something that is a crystalline solid and has a very high pH, it's probably this stuff. If we have something that's a crystalline solid that dissolves easily and conducts electricity, okay, and has a pH of 1, it's probably this stuff. All right, everyone following me here? These are the things we have to know in order to properly identify these compounds. All right, so like I said, bases will typically get us bluish colors on litmus paper. All right, and they have a pH of higher than 7. Okay. Everybody all right with that? All right, so we'll stop it there, and then I'm going to talk about how you're going to put your lab reports and stuff together here.